Good morning, guys. It's nice to see a jam-packed room, but it's a small one. Nevertheless, the story doesn't change. It's exactly the same story I'm going to tell you guys. Before I get into this topic, I want to ask you a few questions. Are any of you working already in predictive maintenance? No. Are any of you, of course, my team, of course, does work on predictive maintenance. I can imagine that. Very good. Now, let's say before jumping into predictive maintenance, you also need to understand a bit of ASML. So let's start a bit slowly with ASML, what we do at ASML, and why predictive maintenance is a tough thing in general, and at ASML it becomes even tougher, and what do we have in place today. So it's not only about predictive maintenance, it is also about sustaining predictive maintenance at ASML for long term. Let's see if this works. Introduction to ASML, a very simple thing. What we do is we make machines to print chips. That's all what we do. And even simpler, the technique what we use is even much simpler is there is a pattern on a mask. We need to take this to a wafer. That's the most basic fundamental thing we do at ASML. The problem comes when you have this machine, or yeah, I call it a machine. It is not anymore a phone because of the reason when you start looking inside it. This is the A8 chip from many years ago. If you start zooming in, you will realize what is happening inside a chip. If you are now you are at micrometer level, you are going deeper and deeper. You are looking at a city with roads with many different constructions. It's three-dimensional. You can see these are all the silicon layers. You have a complete construction. It's much more beautiful than what you see in New York. It is much cleaner, definitely, than New York. So you can see that the dimensions which we are dealing with is 15 nanometers. Now that is our critical dimension, and our overlay is 4 nanometers. So you cannot make a mistake more than 4 nanometers, then things doesn't work. And the feature size which we are talking about is 15 nanometers. This is the feature which we are talking. This is imaging, purely what we do. This is the hardware printing what we do at ASML. Now, again, now zoom out a bit. Started in 1984, now almost 2023. At this time, when we started imaging with our past 2000, the resolution was micrometer level. It was our hair is around 50 microns. The resolution was around 1 or 2 micrometers. Here now we are talking about 14 nanometers, 13.5 nanometers. So that's the improvement that went through the imaging. That means that that little machine over there has become pretty complex. I will show you in a minute how complex this machine is. And where are these machines used? In a holistic landscape. This is your wafer, not your wafer at that point. This is your phone. Before the phone comes out, you have to go through a series of steps. That's just pure silicon wafer. It goes through several steps and then enters our machine. Once it enters our machine, there is a imaging done, as I showed you. The first features are set in. Then there is a yield star, which is also our machine, which does the control inspection, how good the overlay is. And then if things are okay, things we go to the next step. Sometimes we have to loop through many times before the wafer is finished. It takes roughly around 2 to 3 months before the final chip is ready. This is not our work. We only make these machines, but this is all done in the fabs. Now this is also the yield star. It is after inspection, everything is done, everything is okay. And then finally there is a HMI machine, also part of ASML now, which is looking into how many defects are there, what is the yield. So this zoo here, this is what ASML products are. And these machines are supposed to function at the best physics that is put into them. There is we need to guarantee that this performance is round the clock, 24/7, round the year. If there is a mistake, the chips are not working, then the final yield is not okay. Then it's going to impact big time throughout the rest of the world, or let's say there will be impact for our end customers, which we don't want. Now, how do we make sure that everything runs well? Let's understand then one more time at our latest UV machine. If you look at the latest UV machine, the NXE machine, it's roughly around 180,000 kilograms. This is a Boeing 747. It also weighs exactly the same. We need 3 of them to ship one machine to the customer side. Somebody likes Mini Coopers, so in terms of 140 Mini Coopers, 20 years of R&D was put into it, and then there are interesting part is somewhere around 15,000 sensors are there. So that means that it is streaming 4.5 terabits per day. It's a lot of data. So when you get data, what do? You have this data science community. You think of products that you can build on the top of this data. That's exactly what this talk about. So use this data to start predicting the performance and the maintenance that might be required for this machine, so that it always performs at its best. Now, just a small advertisement. We are always active in the PyData community and also at ECML. We have been organizing quite a few workshops at ECML as well. So next time, in addition to PyData, you can also meet us at ECML as well. Now, a bit more about the landscape of data science at ASML. I only told you about what we do with respect to the machines. It starts already with the supply chain. You can also think about supply chain analytics, and in the factory, when we are assembling our products and integrating and testing, there are also opportunities like factory diagnostics. And this is during the fab, during the semiconductor manufacturing, this is where predictive maintenance falls. There is also defect detection and root cause analysis, performance optimization, and also surrogate modeling, where we also use machine learning algorithm. In all these things, one of the main data science challenges is high dimensionality. The data is high dimensional. It's also physically complex problems. You want to model physically complex problems, and the models which we build needs to be interpretable. That's also a challenge for us. You can't just build a black box model, because your domain expert or your fab engineer need to understand this model at a great level so that they can use them. Lastly, a few more things about the machine, then I will zoom into the data science part.
Hi, I'm Richard, and I'm going to tell you about the most important tech company you've never heard of. The name of the company is ASML, and they make machines that are used to create microchips. I'll share 3 striking facts about these machines, all in the next few seconds. Which brings me to the first fact. ASML machines generate extreme ultraviolet light by hitting a molten tin droplet 50,000 times per second, twice, with a laser beam. And that's hot, hot, hot! In fact, the plasma that's generated is hotter than the surface of the sun, which is 5,500 degrees Celsius. Chips keep getting smaller and faster. Thanks to ASML, the most advanced chips easily top 100 million transistors per square millimeter. The structure on these chips are just a few nanometers in size. Just as a comparison, a human hair has a diameter of 90,000 nanometer. That's mind-blowing, right?
So to put it in perspective again, this is really very sophisticated machine. So predictive maintenance in general is challenging. This was my opening statement. Now you want to do predictive maintenance for these machines. So the challenge starts here. Let me go into, okay, slides are a bit corrupted, but it's not a problem. A bit of landscape. Where does predictive maintenance come within the ASML perspective? This is the time, and this is what the probability of a maintenance. The maintenance might be needed for many different reasons, but let's look at in this perspective. When the machine is shipped to the customer side, the machine is assembled, it's ramped up, it is producing wafers. This is what our end customers, or we also want the machine to be. Our machine is built with lots of feedback loops, already thought of many different scenarios. They are very strong. At certain point, feedback loops trigger in if there is degradation. And there is the first performance impact. It could be anything. There could be a first performance impact. And at a certain point, very rare, but this happens, that the equipment goes down. But these are really rare events, right? Now, this is where the impact happens, and then we know at the ASML, whenever this happens, we know how to deal with them. We have to bring the part, bring the engineer, and then bring the system back to production. Now, the business opportunity for predictive maintenance is here, to know in advance what is going to come ahead of us, not only the performance, but also the equipment diagnostics situations, what might be needed. So why do we do that? Of course, we want to reduce the unplanned downtime at the customer, and we also want to prevent that escalations. We have many smart engineers, but it's never sufficient because when there is an escalation, we have to start working on it because we need to bring the machine back to production. If you know in advance, we can prevent some of these things. Now, how do we do that? This is something I want to hand it over to our data scientists. How do we start doing machine learning at ASML? I will come back to you in a minute. Hamideh?
Thank you. Thanks, Anjan. Yeah, so when it comes to the machine learning and data science, we earn our knowledge from active learning with human expert in the loop. We at DSNE, Data Science and Engineering, have a very close collaboration with various domain experts from any step of modeling, from data labeling to model training to model evaluation. But how it works is something like that the old data, the historical data are collected. The domain expert together with data scientists study this data very precisely to understand about the status of the machine. And then a data scientist will train a machine learning by this historical data. Of course, there are a lot of challenges when we want to train the model, we have to tackle. And then when a new data from new machine is coming, this trained model should help us to understand if the status of the machine is about to need a maintenance or not. And to close this loop, we need to test and validate the performance of this model, again with domain expert and also together with data scientists. So this is a continuous learning loop, and it will get several times until the time that we are confident that this model is ready for industrialization for the end user. To a little bit show you how visually show you that how it works, we want to show you a video. But before that, let's see what we want to watch after some seconds. In the right side, you see a green and a red area, which is about the status of the machine. Red means that the machine might need a maintenance, and green means that machine maybe doesn't need for any maintenance. And in the right side, you see the component 1, which is representing the red area, and component 2, which is representing the green area, and they will show you the risk probability of either red or green area. So now I want to pause for a video. I will leave you for a second to watch this video, and then I will come back to that if it works. Yes. Okay, so maybe one more time if we can pause. So this is about the live data. The orange one is a live data. It's a new data that is coming from new machine. And we see that is going through the red area, which means that the machine might need the maintenance. At the same time, the risk probability also is going up. The risk probability of this red area is increasing, which means again that maybe the machine needs for the maintenance. If we are in that status, then the local CS have to help for the maintenance, and fortunately, the customer would be happy with this action. Of course, after all of this phase, we need to validate and test the performance of the model, and also we need to study what model wants to explain. We use a lot of metrics, a lot of criteria to validate this performance. For simplicity, we are just showing you the confusion matrix, which is simply about comparison between the predicted labels, which is coming from trained model, and the true labels. But of course, it's not just about the numbers. We again validate these numbers from confusion matrix or any metric, again with domain expert, and to make sure that this is actually correct numbers. Another important part is the feature importance. So we want to tell the customer or the end user that which feature, which parameters of your machine for the specific failure mode is having the most contribution to predict something, whether you need to do the maintenance or not. Instead of just looking a bunch of parameters, we can just tell them that which one is more important. So this is the whole story or short story about the data science part.
Thanks, Hamideh. So I'm, let's say, have quite a good data scientist. We have been already developing models since a while. We built these models, but there were other challenges. One of the big challenges was about bringing this model to the market. This is where a big challenge was. I will tell you what this is in a bit. So as Hamideh explained, this is, let's say, a predictive maintenance model. It goes through several steps. There is data, and then there is domain knowledge coming in through the labels, feature engineering, feature selection, model development, and industrialization. We figured out that we do these things very well. This is a story also from some time back, so some of the gaps which we have closed. So once the model is industrialized, this is used by a field service engineer where he is looking at a dashboard where he gets, as a function of time, he gets a risk probability for each component. Now he gets the risk probability whenever it goes at certain, whenever it goes 0.5, or whenever he has a traffic light, he start digging into it, and then if he takes action in the right time, he can prevent it down. For example, here this was just a test case where there was a component was had needed a replacement, where the model could predict well in advance. So the domain experts were very happy. Hey, nice, we could teach a stupid robot how we think on a day-to-day basis. So they were very happy that they have more students, and they could teach more of them to be further fine-tuned. Now the challenge was it used to take a really long time to industrialize, to do from here to here, where there is value created for ASML. It's great that we build data science models. We also need to bring it to the market. This is where the biggest challenge was. So we were thinking, how can we solve this problem? We were wondering, we were looking into each of the different phases. There is a feasibility phase, there is a POC phase, validation phase, and industrialization phase. Where are we losing time? Where could we improve? And then we figured out we were losing time in almost all the places, and we had to see what are the subtopics where we are losing time. There were challenges at data quality. There were challenges. We were doing a lot of manual work, and we were also using multiple platforms to develop and industrialize our models. So data quality, acquisition of the labels, starting from there. If you have a few domain experts, there are inconsistencies between the domain experts and how the labels have been given. There might also be some inconsistencies there. Starting there, and then the manual work like bookkeeping, what data is labeled, what data is not labeled, where is the code, how is it checked in, how are we testing the models, functional testing, how are we adapting these models if there are new use cases coming in. And then having two platforms, it's also redundant effort to maintain two different platforms, one maintained by IT, one maintained by us for development, and having different competencies between the development team and the engineering team. So then we started looking around, and then we asked people, hey guys, do you know what is the solution? And then one of the solution is MLOps is the solution. This is what Google is using, this is what Amazon is using. So we have to embrace something new. And then what is this new part? MLOps is, let's say, somewhere standing in between the machine learning, DevOps principles, and data engineering principle. The idea is we want to streamline the process of taking machine learning models to production. So everything has to be improved at each and every step, and our way of thinking, our regular way of work has changed. So from manual labeling on Excel sheets or manual labeling in PowerPoints, we went to smart labeling, started using some smart labeling tools, and then automation. We started using the DevOps practices, for example, CI/CD, where most of the tests are done inside. And then we also have one single unified platform. Once the model is developed, there is no need to put another wrapper around it because it's already sitting inside a nice container. It can be deployed easily. So it enabled the most important part for bringing any machine learning model to production, the fast iteration. You need to build a model, and you need to check if it is useful or not. We can do now with this fast iteration. If there is a problem, we can fix it, and then we improved almost 8 times our time to market. Let's say it took months, and then we went to weeks. I will describe a bit more about what the solution which we have in place today with a very high level architecture which reduced our time to industrialization. Let's start with our customers. Who are our customers? Our customers are within ASML, it is CS, customer support, and also development and engineering teams, and also other data consumers. This could also be outside ASML or somewhere internal ASML. So there is only one single platform, but it is divided into two pieces for many different reasons. There is a development part and there is industrialization part, exactly same copies, but the authorizations who can access different pieces are different. The first part is integration. uh, Three fundamentals, right? You need the data, you need the methods, and then you need the knowledge. You can't build blind machine learning models in ASML. You really need to understand the data to the core before you start building the models. So we really need to integrate the functional knowledge existing at ASML. Now, once you combine all these things, you have the first data set, that's the labeled data set. Previously from here, we used to go already do the modeling. Now we started changing it. There is a label inspection tool, automatic label inspection tool that says, hey, domain expert, there are certain inconsistencies. Do you want to look back at it? Or we pop up, if he labels one machine, there is a similar machine with a similar behavior. Do you want to also label this? Now that helps to go in these loops faster and converge to the right accurate labeled data set. And then you can continue the remaining steps to do the feature engineering and do the model development, and the most important part, the validation. At this point, you can say, my model is good. You can stop at this point because we have a good handshake with CS, or we need to go back, or we need to further go back here. But these are all, let's say, closed loops. Everything is already in place. You should be able to request the right person to do the right thing, and then everything comes in place in a short period of time. Now, with the click of a button, the model is ready, and you push it, goes to the CI/CD, and then the pipeline is deployed in the production phase, where there is a single pipeline for each failure mode. The pipeline is working, trying to predict whether a specific failure mode is going to appear in the next few months or not. And then the output is consumed by our consumers. Consumers, when they consume, they always have feedback. This is something very nice, right? This is in the beginning. I was wondering, too much feedback might mean that we only will be integrating the feedback, but the fact that the feedback started coming in faster, you can actually improve your models much faster. So there is customer feedback. Once the customer feedback comes in, what you can do is you can monitor how good your model is behaving today. Is the model behaving as expected, or is there some performance issues? Once you know how good your model is behaving, because here you have an expectation, you transfer it to production. Now it gives the real beta test value. If you have a precision and a recall of 90, here you could already see probably the recall has dropped to 70 or something like that. Now what can you do? If you have a continuous training pipeline in place, the continuous training pipeline will automatically trigger and deploy the new model, so that you don't have to worry about it. If it is just a small data drift issue, that will be fixed. Sometimes it can be possible that that's not sufficient. You have to go all the way back to redo this. But many of these things are in place. So basically, the problem has changed, or the component has changed so much, you have to relabel the data, and you have to redo this whole process. This is what we call the MLOps solution that we have placed at ASML, where from end to end, everything is now, let's say, automated. We are using the new MLOps principles, and this saved us a lot of time. In addition to that, there's pipeline monitoring. This is exactly useful for me to sit on my control room to see, hey guys, there is a pipeline that is red. That means that one of our customer is not seeing the results as expected. So we can also immediately figure out what is happening there, and our IT teams can help us bring the pipeline back to production. Through this, by mindset change and also the way of working change, we went from, let's say, months to weeks to build a solution and to productize it. Now, let's say the machinery. Some of you might be very interested in what is the machinery behind behind this architectural picture. Of course, we are in Google Cloud Platform. We use AI platform. We use Dataproc for our Spark pipelines, and cloud source repository where our code is stored. And we are of course using container registry where our containers are stored, cloud build for our CI/CD part. This is also something interesting, maybe some of you might not know. We always try to reuse whatever we build. That also helps us not to build everything from scratch. So we have an internal solution called a dbox, where we put our reusable blocks. So every data scientist, whenever he builds up something, the others can use the same script or the same function, so that they don't have to start from scratch. Now, as you see here, again here, the AI pipelines here is no different from the other one. It's basically the same pipelines that will help move from platform A to platform B as soon as possible and run it there. So this is let's say one of the last slide I have. The I told you about the training pipelines or the continuous training pipeline. It's hard to see. It's highly pixelated for the purpose that you don't read it. Uh, as you can see, this is in place. So what it does is basically whenever there is a training needed for a specific machine, it goes to the training pipeline. So there are multiple scenarios that are I wouldn't call it auto ML, but there are multiple machine learning algorithms. We would like to try it out with multiple hyperparameters, and we spit out the best model. And then we would like to use those best models in the prediction pipeline, the pipeline that is for a specific failure mode. It is predicting the output, which will be published towards the dashboards, where the output will be used by our field service engineers. Now, you might be wondering, how did we transition? This might be also something interesting for some of you. When we started using our laptops a few years back, we started building our models in our laptop using Jupyter Notebook, and then we were trying to deploy in our high performance computing center. It used to take, let's say, X amount of time. When we learned about MLOps, we of course didn't go directly to it. We want to test out the waters, right? We started moving MLOps 0, MLOps 0 plus, now MLOps 1 plus. You could see whatever it was, X, it came down significantly down. This is really in weeks now. To from the intake of a specific use case or a specific failure mode, we understand it, build a model, and industrialize it. Now we are talking about sustainable predictive maintenance. If it really takes months or weeks, because ASML is also evolving so fast, the product itself can change before you build a model. So it is really important that we build models and industrialize in time so that the value is delivered at ASML. Now, a conclusion, I think, let's say many of you might be working on machine learning products. Never ever try to succeed in the first attempt. You need to iterate. Iteration is key, and fast iteration is key to success. Industrialization of models is also important. Keep that in mind always. For us, it worked by embracing MLOps methodology. We could go from months to weeks here. Specifically, let's say for us, this is also within ASML advertisement. We started building only a couple of models. Now we are more than tens of models that are in production, being used. Our customers are happy. We are still counting on with this new thing in place. We are, let's say, looking into the future to receive more requests to build more predictive maintenance models. This is a slide I will play in a bit, but if you have questions now, I will take it. Thanks. I saw a hand over there. Yeah. Mm-hmm. I have to repeat the question for the online audience, if there are any, or future ones maybe. Uh, do we train models centrally, or do we adapt the models locally to protect the customer information? Very good question. We do both. Depending upon what we are talking about, what failure mode, and what is the model going to do, what data we use. There are certain models where we can use ASML specific knowledge, which can be built here. When we have to use customer specific knowledge, we build at the customer side and deploy it at the customer side. Both are true. Yeah, good question. Go ahead.
So active learning is super useful because you might have a machine learning model that can suggest, like, hey, check these examples first.
Yeah.
Downside, though, in my domain, NLP, is that it can also get stuck in a local optimum because the model believes that the world works a certain way. So you've got that little conflict between what the model thinks and reality. Is that a concern for your machines as well?
Yeah. 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 I think you're absolutely right. If it is, it can, we have it in place to some extent to help our domain expert, but it can also really annoy them to continuously pop something that is not okay. Uh, so it is a bit of pragmatic approach there. When you know things are not working, you want to interfere. So the active learning approach, there is an algorithm that always spits out, but you can also immediately cross-check if it is really suggesting the right suggestion or not. This is when the data scientists generally interfere and help out. But you are absolutely right. It can sometimes, instead of helping, it can also cause damage to the original purpose. On a day-to-day basis, I cannot tell on what percentage it is. Generally, the data scientists sit with the domain expert and then try to explain the results. It already helps to look at them together and then read the readings. If the data scientist observe that the let's say the pop-up by the active learning algorithm is not okay, he has to meddle with the algorithm. Yeah. Mm-hmm. Yeah. Mm-hmm. Yeah. Yeah. The question is, do we have one model for all the landscape, or do we have separate models for each different product? This is a very good question. Yeah. Yeah, yeah, yeah. I cannot be completely honest here because this is IP protected. But let me see. The answer is there are universalities when you look at the component level. You want to maximize this universality. So this is where understanding that component and then data helps a lot. And when you look at this data, you make choices. Do you want to build one model across the fleet? Is it the functionality is the same? But in some cases, it might not be the case. That is when you want to think of certain hierarchical modeling kind of situations. Yeah. So that's a brief answer for your nice question. Yeah.
Maybe in the same domain, if you have one machine and has many different failure rates,
Yeah.
And maybe now a new type of failure pops up.
Yeah.
Do you do any kind of transfer learning to make it faster to train this new failure rate?
Yeah, yeah. Very, very good question. Do we use transfer learning to adapt from failure mode A to we do it a lot in two different ways. Transfer learning in the model and also with the data scientists and also in the with the experts as well. So there are components which are very close. The functionality is similar, especially with the product evolution. The when you go to a different product, the model which you have built for this product, and then when it is adapted in the new product, you probably don't have enough data there. So you can't you can start from scratch, but the quality of model you can already guess it might not be the same. This is when you can already take the models which you have built today and adapt it to the future use cases through transfer learning. Yes, we do use those concepts. Yes. Yeah. Yes, then let me play the video. Can you help me play the video? Because this is also something it might be interesting for some of you.
You get to say that you're working with some of the most advanced machines in the world.
You see people from different countries. That's what I also enjoy.
It's fun that you can do something with a large group of people outside of work.
Problem solving is my job. There is a mechanical problem and I have to solve it by design.
I'm a system install engineer, so I'm integrating the system and installing it at the customer site. This is our football team. We're going to compete in a competition in China in the summer, so it's really exciting. I moved over to Holland on my own, so I didn't know anybody. But this is a great way to meet people that have the same interests as you. Every day is just learning something new, always pushing the boundaries of your imagination. You never thought you'd be doing something so high-tech.
I'm an imaging applications engineer. I basically test the performance of the machine before we ship it to the customers. The place where I come from, India, is a very small town. I did my PhD at the University of Twente. After that, I joined ASML. ASML is always open to give chances to meet different cultures.
I'm a mechanical designer. My task is to design, build up and test tooling for our latest EUV machines. During my work, I think a lot. I design with my head. It all starts up here.
To keep my head clear, I really need to be active. So this helps me to focus and gives me a lot of pleasure and satisfaction.
I'm a flex worker here within ASML. I work via external company, but still I feel like being part of ASML.
I'm an integrator for the immersion project, specifically the immersion hood. I make sure that the component actually works in the machine and works together with the other technology that's also there. When you talk to other departments and you see what their problems are, you see what they are dealing with, struggling with, you also learn a bit about them. That's, I think, the most challenging part for me, the most fun part. I'm involved in an organization called Young ASML. I organized a trip to Zeiss. Zeiss is the supplier of our optic equipment. So we organized a trip with 50 people there and we went for a visit. It was really cool.
I'm on my way to Schiphol Airport, flying to South Korea to Samsung. I'm installing a machine over there, one of ASML's leading products. My job is so cool and I get to travel, so it's amazing.
So it was the reason why I played is I still have open positions in my team, and also data science is a quite active, growing community in ASML. There are roughly, let's say, 100 core or slightly more than 100 core data science data engineers and machine learning engineers. There are quite a few citizen data scientists, and this community is quite vibrant. We are part of a data department within ASML. You can definitely look up for the open positions we have, and it is cool to work at ASML. Join us if you are interested.
Thanks everyone. That was it. So if you want to run a marathon or wear a funny hat, hit up these guys about ASML.
Thank you.
And feel free to move on to your next sessions now.